Hello everybody again. So here's the do now. There are some specific things that I want to point out to you guys, but go ahead and do this. If you want an example of this, what it's really asking, find the limit of the expression as n approaches infinity. We're talking about the limit, excuse me, as n approaches infinity of n absolute value of x over n plus 1. So looking at this, since I'm limiting n and not x, x here is a constant, so I can move that x out of here, and I have the limit as n approaches infinity of n over n plus 1, and I'm alright. Technically, we would have to do L'Hopital's rule on this, and if you look at my answer key for the homework that I'm going to assign you from this lesson, you'll see I use L'Hopital, but I'm alright with you just saying this is 1 right here, so this becomes absolute value of x. So pause this, try to do these. Remember, anything that has an x can be just slid out of the limit in here, and I'm going to put the answers up even though you have access to the answers. I'm going to assume that some of the difficulties that you guys have here are like whenever these factorials come into play. I mean, particularly down here, I'm going to give you a nice little trick on doing factorials for that one. Like this, where I have 2x plus 1 to the n plus 1 over 2x plus 1 to the nth. Remember, since you have the same base, you can just subtract same base. You can subtract the 2 is in the bottom, the 2x plus 1, n plus 1 minus n, puts it in the top here. One particular thing that I do want to dwell on here, this 2n factorial over 2n plus 2 factorial, I mean, really, you should have something like absolute value of the limit as n, not x, n approaches infinity of 2n factorial over 2n plus 2 factorial. I'm really just going to dwell on that guy right there, because looking at this, 2n factorial really means 2n times 2n minus 1 times 2n minus 2 ... multiplied all the way until you get to 0. Well, that's going to take forever because n is infinity. But on the bottom, we have 2n plus 2 factorial, which would be 2n plus 2 times 1 below 2n plus 2 would be 2n plus 1 times 1 below 2n plus 1 would be 2n times 2n minus 1 times 2n minus 2 ... What's interesting here is all of those terms end up being the same, and this ends up being absolute value of x over the limit as n approaches infinity of 1 over 2n plus 2 times 2n plus 1. So you can actually see there you have infinity times infinity on the bottom, so this ends up being absolute value of x times 0, which gives you 0 here. That is going to extend whether you have n plus 1 factorial over n factorial or n factorial over n plus 1 factorial. You just want to think in this process because those ratios are going to come up today. So like if you have n factorial over n plus 1 factorial, that's the same thing as n times n minus 1 times n minus 2, etc., etc., etc. In the denominator, we'd have n plus 1 times n minus 1 times n minus 2, etc., etc., etc. All those bad boys are going to cancel off, and you're left with 1 over n plus 1. Obviously, if you have n plus 1 factorial over n factorial, it's exactly the reciprocal on there, so you'd end up with n plus 1. So that's just a trick that you're going to have to know for today. There's the homework that I assigned last class, or last lesson, whatever. And right here, section 9.4, Radius of Convergence. So I was looking at all of the stuff that AP said we need to know for this unit, and we don't need to know radius of convergence. So we're going to do a couple of radius of convergence problems, but we're not going to focus on radius of convergence that much. But there are things that pop up in this section that are on the test, that being the nth term for divergence, the direct comparison test, the ratio test. Those are all things that you need to know. So the series that are of the most interest to us are those that converge. So a great question to ask, does this series converge? And if it does, for what values of x does it converge? So here, this section is really about, does a function converge, yes or no? Or if it's a power series, for what values of x does it? So the first thing that you have is the nth test for divergence. It is a nice, quick way to quickly determine if a function diverges. Most often, I do not write down the nth term for divergence unless it proves that a series diverges. So you might want to write it down. Summation from n equals, it doesn't matter what the initial index is here, it's n equals anything to infinity of a sub n diverges if the limit as n approaches infinity of a sub n fails to exist or is not 0. Basically, what this says, to possibly converge, the limit of the nth term has to be 0. Not 0 does not it's definitely divergent. Unfortunately, it doesn't prove convergence, so this is why I say, unless I see that a function or that a series is going to diverge, I don't actually write this test down. So looking down here, we have the summation from n equals 0 to infinity of n factorial x to the nth. Well, I look at that, and I see when I get to infinity, this is just going to produce infinity times x to the nth. That's just going to be not 0. So that's where I would say, okay, I'm going to use the nth term for divergence. And I would just put down limit as n approaches infinity of n factorial x to the n not equal to 0. So therefore, the series n equals 0, summation from n equals 0 to infinity of n factorial x to the n diverges. And on your homework tonight, you're going to have to justify this. So you're just going to say, by the nth term test. So it's a good test if it works. If it doesn't work, then you kind of have to look for other stuff. And what I mean by doesn't work, I mean you get the limit is 0. That does not say it converges. Right? So another option we have is something called the direct comparison test. It is for a non-negative series, so we're not looking at alternating series. Actually, proving an alternating series diverges or converges is really easy. But for a non-negative series, if every term of a series is less than the corresponding terms of a convergent series, then both series converge. If every term of a series is greater than a corresponding term of a divergent series, then both series diverge. And these are supposed to actually be color-coded, where the known is, you can kind of see it's a slightly lighter gray. So this series we know. Anything that we don't know underneath of it, we don't know what it converges to, but it has to converge. And down here, these are like light gray. I think it was like red versus blue. But if you have a known series that you know diverges, anything bigger than it also has to diverge. All right. So that comes into play. I think on your homework tonight it specifically says use the direct comparison test, and then the one right after it is a direct comparison test as well. But that one's using absolute convergence, which we'll get to next here. But to prove that this converges for all real x, what we look at here is we have the summation from n equals 0 to infinity of x to the 2n over n factorial squared. Well, I look at that and I notice that this function is actually similar to the series for e to the x. E to the x is equal to the summation from n equals 0 to infinity of x to the nth over n factorial. Well, looking at this, I can write that as x squared to the n over n factorial. I know I did leave off that squared. That's going to come up here in just 1 second. But now this ends up being exactly this series, which is just e to the x squared. So I know this converges. As long as this is smaller than this, then this is going to converge as well. And looking at this, the only thing that I did to change this series to the e to the x squared, I deleted that squared. And now since n is going to be 0, 1, 2, 3, 4, 5, 6, I'm unsquaring a positive integer. Unsquaring a positive integer makes this number smaller. When I make the denominator smaller, I make the fraction bigger. So all of these terms have to be greater than this right here. Since this converges, and the summation from n equals 0 to infinity of x to the 2n over n factorial squared is smaller than a convergent series, it also converges by the direct comparison test. And yeah. There's another test. This one is a little bit stronger because it allows you to prove convergence of a series. The only thing that stinks about this one is you kind of have to luck into having a known series that you can compare it to, which you don't always have that. So there's other things that we can do, like absolute convergence. On that last test, it said that you had to have excuse me. It was just a tickle in my throat. I swear I'm fine. To use the direct comparison test, you need to have a positive series. The way to get positivity is you take the absolute value of every single term. And if a series, if you take the absolute value of every term and you prove that that series converges, then we say the series converges absolutely. And here is a wonderful theorem titled Absolute Convergence Implies Convergence. And what it says is, if a series converges absolutely, then it converges, period. So if a series converges absolutely, then it converges. Where would I ever use that? Oh, here's a nice way to use it. So I see I've got the summation from n equals 0 to infinity of sine of x to the n over n factorial. I want to prove that it converges. First off, I'm telling you it converges, so it's going to converge. Next, I recognize that sine of x, well, sine oscillates between -1 and +1. So I don't know whether that's going to be positive or negative. Even further, this is bouncing back and forth between evens and odds, so it could keep its negativity, it could take away its I don't know what's happening here. But what I do know is summation from n equals 0 to infinity of the absolute value of sine of x to the nth over n factorial. Well, I take the absolute value, and since this is between -1 and 1, this quantity, sine of x, now, since I'm taking the absolute value, has to be less than +1. So this, I'm actually saying my numerator is smaller than 1, so the whole fraction is going to be smaller. I have summation from n equals 0 to infinity of 1 to the nth over n factorial. And I know I don't need to actually put 1 to the nth. 1 to the nth is just 1. But looking at this, again, this fits into that format of summation from n equals 0 to infinity of x to the n over n factorial is equal to e to the x. This is just e. E to the first. So this that just converges. It converges to e. Well, I know this is smaller. This sum is smaller than e. So this converges to some number. It's not smaller than e. So the summation n equals 0 of the absolute value of sine of x to the n over n factorial. And I think I'm being extremely verbose in writing this. Converges absolutely by the direct comparison test, and thus, again being verbose, summation from n equals 0 to infinity of sine of x to the n over n factorial converges. Right? There we go. Boom! Yay! Woohoo! Yay! 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 Oh, there it is all written out. Okay. Now, convergence theorem for power series. This is something that is not going to be on the test because it's about the it's the radius of convergence. So the series converges over some finite interval, the interval of convergence. There is a positive number r such that the series diverges for the absolute value of x minus a greater than r, but converges for absolute value of x minus a less than r. The series may or may not converge at the endpoints x equals a minus r and x equals a plus r. The series converges for every x r equals infinity, or the series at x equals a converges at x equals a and diverges elsewhere. The r is equal to 0. The number r is called the radius of convergence. And if you remember back to when we did the geometric series, there was a graph that showed the Maclaurin series for the geometric series would converge right between r equals -1 and 1, right between the values of x equaling -1 and +1, and it was bad outside. You can also look back at the Maclaurin series for sine that I graphed in the last video. That shows that as you add more and more terms, you get a better and better approximation of sine. Yeah. Again, radius of convergence not going to be on the test, but this part will. And this allows me to determine what r is in certain power series. So the ratio test, it is a wonderful test for determining if a series converges or diverges. I've seen some people just lean on this test for checking convergence or divergence, period. But for a series, if the limit as n approaches infinity of a sub n plus 1 over a sub n is equal to L, then if L is less than 1, the series converges. If L is greater than 1, the series diverges. If L equals 1, the series may or may not converge. And basically what we're trying to do here is we have the ratio of the term after the last term to the last term. And if we take the term after the last term and divide by the last term, we should get a ratio. If the ratio is less than 1, that means the top number is smaller than the bottom number. We're just trying to confirm that the series, the terms are getting smaller and smaller as we go into infinity, and that's how we can get convergence. If L is greater than 1, well, that just means that the terms are getting bigger and bigger, and thus the series is going to have to diverge. If L is equal to 1, that means they're the same at the end, and, well, we're going to have infinite ones added together, or infinite numbers added together. You actually have to do some other tests for that. So that's the one time that the ratio test kind of sucks. I'm going to scrap a couple of these because they have you finding the radius of convergence. I'm scrapping this one. You can see the work over here, though, if you want to dig through it. We do want to find this one, though. Find the radius of convergence of the summation from n equals 0 to infinity of n x to the nth over 10 to the nth. Anytime you see find radius of convergence, you are going to jump immediately to L is equal to the limit as n approaches infinity, and you're going to have a big fraction. The numerator of that fraction, again, what I'm doing here, I'm doing this ratio test. You have that written down on another page. You can flip back and forth to that. The numerator is supposed to be a sub n plus 1. So that is just going to be n plus 1 x to the n plus 1 over 10 to the n plus 1. And technically, on my notes over here, I put absolute values in here. There's one particular reason why we have to do that in this case. It's because of the x here. Everything else is going to be positive because I'm plugging in n's up there. So, yeah. Over, and we just want to take that nth term. So nx to the n over 10 to the n. So this is one of my favorite things to do. It is super cool. So again, you plug it into the formula, and then you just have to go off and do as much math as you can. That's why I like this. Limit as n approaches infinity. Now again, the only place where negativity can come up is in that x or that x, because everything else is positive. We're starting at n equals 0 and going up to infinity. So n is never going to be negative. So here, I'm looking at, let's see, n plus 1 magnitude of x to the n plus 1 over 10 to the n plus 1. So note, that's just the numerator, and I kind of adjusted my lining up of the fraction, because here, since I have this nested fraction, I want to make this 10 to the nth over n x to the n, magnitude of x to the nth. I just took the reciprocal of the denominator, and absolute value only goes around the x's. Now I just look for stuff that I can do. Well, limit as n approaches infinity. That n plus 1 divided by n, there's no way that I can do anything with that, because, you know, plus 1, not plus 1. So this is going to be n plus 1 over n. Now something else that I see that I can do, I've got 10 to the n plus 1, and I've got 10 to the n. Notice how, same base, I can now do n minus the quantity of n plus 1. That becomes 1 over 10. Times, and last but not least, same base of absolute value of x, n plus 1 minus n gives me absolute value of x. Because of the properties of limits, I can take that absolute value of x, toss it out front like I told you guys on the do now. Limit as n approaches infinity of n plus 1 over n times 1/10. Again, technically this is infinity over infinity, so we would have to L'Hopital it, but I mean, really, it's linear over linear. That just becomes 1 times 1/10. This becomes 1/10 times the magnitude of x. Now going back over to Chahira, as long as that value is less than 1, the series converges. So, less than 1. Now to find out the radius of convergence, I have to actually find the almost the interval of convergence, because I see absolute value here is less than 1. That means 1/10 of x is definitely less than 1, but it's also greater than -1. And now I can just multiply across the board here. I have -10 less than x less than 10. And find the radius of convergence. That R, again, not going to be on the AP test, but it's good to know anyway. The radius of convergence is how far out you go from the center of the center of the series. I can look back up here and see the center is 0, or I can actually look here. The radius of convergence is going to be half of the interval of convergence. So 10 minus -10 divided by 2 gives me 10. Radius of convergence is 10. There you go. And one other radius of convergence problem that we're going to do is this one. Yeah, I don't want to do too many more radius of convergence. I do want to prove convergence. So we'll take a couple of problems from the book, and I'll just do those for you guys. But looking here to find the radius of convergence, again, it says find radius of convergence. So we start with L is equal to limit as n approaches infinity, big so-and-so fraction. I'm going to have n plus 1 factorial over n plus 1 to the quatroth times x to the n plus 1. I guess put magnitude around all that, although we don't really care about that because we don't care about that for the AP test. We care about that for our own well-being. n factorial over n to the fourth times x to the n, which is going to be equal to limit as n approaches infinity, and the only negativity is going to come from the x. I'll have n plus 1 factorial over n plus 1 to the quatroth times the absolute value of x to the n plus 1 times, now I'm just going to take the reciprocal of everything down here, n to the fourth over n factorial times 1 over magnitude of x to the n. And again, get to this point and just do as much math as I can. Limit as n approaches infinity. Okay, so let's get rid of the easy one right here. X to the n plus 1 divided by x to the n, that's just going to give me magnitude of x. Now let's go for some harder ones. N plus 1 factorial over n factorial, if only we had done that before, times lost my train of thought there for a second. N to the fourth over n plus 1 to the fourth. I mean, really, on this one right here, that kind of, I don't want to do L'Hopital's rule on this one, just because now I'd have to do it 4 times, but I see a quartic over a quartic, I can just do lead terms, so that's going to be times 1, and as n approaches infinity. Okay, this one, we go back to our do now and see what we did. We had n plus 1 times n minus 1 times n minus 2 in the numerator, divided by n minus 1 times n minus, or n times n minus 1. We're just left with n plus 1 in the numerator. And let's toss the absolute value of x out there. Well, limit as n approaches infinity of n plus 1, well, that's just infinity. Absolute value of x times infinity. We want that to be less than 1. That ain't happening. That ain't happening. The only way for this to happen is if x is equal to 0. So therefore, the radius of convergence is equal to 0. But again, we don't care too much about the radius of convergence this year. You will see it when you get to Calc 2. But, you know, whatever. Here's what you really do need to know. And a lot of people just jump right to the ratio test. It works as long as your L is not equal to 1. So looking here, determine if this series diverges or converges. All right? Yeah. I know. Since this is in the ratio test part, I'm probably going to be doing this. Limit as n approaches infinity of, well, here, magnitude doesn't even make any sense in this case, because there's nowhere, like, 2 to the n plus 1 over 3 to the n plus 1 plus 1 over magnitude of 2 to the n over 3 to the n plus 1. Yeah. A sub n plus 1 over a sub n. This ends up being, let's just get rid of those absolute values, because there's no way I'm going to have any negativity. If I had an alternating series, I could toss out the negativity. The one thing there that stings is if you use this to prove an alternating series diverges, you actually can't. But there's such an easier way to prove that an alternating series converges or diverges. We'll get to that next lesson, though. Here, we're going to have 2 to the n plus 1 over 3 to the n plus 1 plus 1 times 3 to the n plus 1 over 2 to the n, right? Just taking the reciprocal of that. Well, it looks like some easy stuff to toss out here. I've got 2 to the n plus 1 divided by 2 to the n. That just becomes 2 times 3 to the n plus 1 over 3 to the n plus 1 plus 1. Okay, so just to write this a little bit clearly, I can put the 2 out front. I got 2 limit n approaches infinity of 3 to the n plus 1 over 3 to the n plus 1 plus 1. Okay, now I get scared on this one. I'm thinking L'Hopital rule here, or I should look for here's a nice little trick. Divide by 3 to the n. Divide by 3 to the n. And this all of a sudden becomes 2 limit as n approaches infinity of 3 to the n divided by 3 to the n becomes 1 plus 1 over 3 to the n. That's just 0 right there. Over, let's see, 3 to the n plus 1 divided by 3 to the n becomes 3 plus 1 over 3 to the n. Oh, that's 0 as well. So I have 1 plus 0 over 3 plus 0. That's 1/3 right there. This ends up being 2/3. Is 2/3 less than 1? Yes, it is. It is. Since 2/3 is less than 1, this converges by the ratio test. All right? Boom, 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 boom. Okay, so before I give you your... Actually, here, I'll just toss the homework assignment up there. I will point out that if you downloaded my flip chart and looked at it, you will note that it says 4 through 22 even on the last page. Change that 4 through 10 even and 30 through 42 even. I changed it because this focused more on finding the radius of convergence. We didn't want to do that. These really focus on testing everything. I think most of them I was able to use the ratio test in order to find out that they converge. So now looking here, I just want to do 29, 37, and 39. That's on page 511 for you guys if you're following along at home. So 29. The question is, does the series converge or diverge? And what test did you use for this? So n equals 1 to infinity of n over n plus 1. The first thing you should always do, and you kind of do this in your head, take the limit of the nth term. Just imagine this says limit as n approaches infinity. If the answer is not 0, the function diverges. So if you're following along in your head here, limit as n approaches infinity of n over n plus 1, that is not 0. Again, technically I would have to do L'Hopital's rule here because I get infinity over infinity. So technically if this was like a scholarly paper that I was doing, like your homework answer sheet that I post for you guys, this would be 1 over 1, which is equal to 1, which is not equal to 0, and thus the series summation from n equals 1 to infinity of n over n plus 1 diverges by nth term test. The directions in the book also say to iterate which test you used here. All right? 37 is the second one that I wanted to do for you guys. Summation from n equals 1 to infinity of n plus 3 factorial over 3 factorial n factorial 3 to the n. Okay, insano. I'm looking at this and I'm thinking the limit as n approaches infinity of this crap in here. I have absolutely no idea whether that is 0 or not. No clue whatsoever. So I'm not going to use the nth term test because it just scares me. Now, looking a little bit further on this, I'm just busting out, this is a little bit of scratch work right here, but I see I've got n plus 3 factorial over n factorial. I don't like dealing with multiple factorials at once. So again, I'm just going through here. I can have that as n plus 3 times n plus 2 times n plus 1 times n minus 1 times n minus 2, etc. over n factorial is just n times n minus 1 times n minus 2, etc. Gone, gone, gone. I can now just change that. Instead of n plus 3 factorial, I can have summation from n equals 1 to infinity of n plus 3 times n plus 2 times n plus 1 over 3 factorial, n factorial, 3 to the n. Okay, gonna get messy now. I'm going to use the ratio test because, again, I think that's the easiest one to use. Limit as n approaches infinity. Easiest as long as it works out. For the numerator, I need to have n plus 1. So n plus 1 plus 3 times n plus 1 plus 2 times n plus 1 plus 1 over 3 factorial times quantity of n. Nope. I didn't have to put the n factorial down there. Why did I put that down there? Why did you guys let me do that? That n factorial shouldn't be there. 3 to the n plus 1 over n plus 3 times n plus 2 times n plus 1 over 3 factorial 3 to the n. Okay, messy as ever. Limit as n approaches infinity of, well, 1 plus 3, I know that's 4. N plus 4 times n. 1 plus 2 is 3 times n plus 1 plus 1 is 2 over 3 factorial times 3 to the n plus 1 all times, let's see if I can cram this in here. 3 factorial, 3 to the n over that garbage. N plus 3 times n plus 2 times n plus 1. Oh, just barely fit it in there. 3 factorial, cancel out. 3 to the n plus 1 down below, 3 to the n up top. Okay. That becomes 1/3. Again, that's from 3 to n plus 1 divided off of 3 to the n. All that's left now is n plus 4 times n plus 3 times n plus 2 over n plus 3 times n plus 2 times n plus 1. Hey, that was convenient that worked out very well. Now I just have n plus 4 over n plus 1. Alright, I should have crossed it off up here, whatever. N plus 4 over n plus 1 when n approaches infinity, that's just 1. I end up with 1/3 times 1. Is that less than 1? Yes, it is. Therefore, the original series, summation from n equals 1 to infinity of n plus 3 factorial over 3 factorial n factorial 3 to the n. Note, I did just go back to the original. Converges by ratio test. Alright, one more that I want to do for you guys. 39. Don't worry, it's not as extensive as 37. 39 is actually really easy. Summation from n equals 0 to infinity of -2 to the nth over 3 to the n. Now, I've practiced with this many times before. I don't even know if the ratio test would work here, because I don't even do ratio test on this one. I look at n equals 0 to infinity, and since they're both to the n power, I make this -2/3 to the nth power. Now, really quickly, since this is less than 1, this would, the limit would be 0. So I don't need to worry about that so much. But since this is in this format, this is in the format of summation from n equals 0 to infinity of ar to the nth power. That's a geometric series. In this case, my common ratio is equal to -2/3. I'm just multiplying by -2/3 each time. I mean, really, a is equal to 1, but I don't need to know that. R is equal to -2/3. The magnitude of R is equal to the magnitude of -2/3. It's +2/3. as long as this is less than 1, it converges. That's from the first section of the chapter. It's a geometric series. Since the common ratio is, since the magnitude of the common ratio is less than 1, it converges. And it just really hurts me to put it as by geometric series. It's just saying by the argument of it is a geometric series. So really, let's just call it the geometric series test. All right, and that's it for today. Goodbye.